Well, welcome back to our final 2 lessons in Quarantine Mathland. Last week we learned about different kinds of transformations. We learned about translations, reflections, and rotations, and on all of those cases, the size stayed the same. So we're going to keep going with our last type of transformation, and that's a dilation. So we're going to kick it off with an application of how it is used in the art world.
Check it out. It's a larger-than-life painting of President Barack Obama. And you know what? The artist that did this actually used math. You see, this painting is a larger replica of a smaller image. In math, we call it a dilation. You know what? I know somebody that uses these in their art. Let's go meet him.
Hey, Luis. Good to see you. This is Luis Peralta. He's an artist here in Washington, D.C., and he does murals. But you can't just paint them straight onto the wall, right? So you use math to make that art.
Yes, one of the things that we as artists do to create murals is we usually do a small sketch, and then we increase the size by projecting the image onto a wall or any surface.
So you don't just start with giant murals, you start with something that size?
That small. This is actually about 4 inches wide, and today what we're going to do and demonstrate is multiply it to about 900%.
Excellent. Let's see how it works.
So Luis is using a dilation right now. He's got that little original image on the projector and the much bigger one here on the screen. So all the proportions are exactly the same, even though the distances and the sizes are a lot bigger. Awesome. And that's one reason math matters.
All right, second to last entry, guys. You can do it, finish strong. So set up a new page or a new piece of binder paper and write properties of dilations. And we're going to look at how do you describe the properties of dilation. So hit pause, make it happen. Okay, so a dilation, like I said before, they change the size, but the shape stays the same. So you could think of like models of rockets being dilations, and they come in 2 versions. We can enlarge them or we can reduce them, make them smaller. And every dilation has a fixed point called the center of dilation located like outside the 2 figures, where if you lined your 2 dilations of each other up like this and you connected the corners together, you'd see like a vanishing point kind of thing, and we call that the center of dilation. And it shows that they're all proportional to each other. Okay, so we got some vocab, so hit pause and copy all this into your notebook. All right, so we got that a dilation is a transformation that changes the size of the figure, but not the shape or the orientation. We're going to keep the orientation the same. The center of dilation is kind of like that vanishing point where the corresponding parts, if we drew imaginary lines, that's where we'd see those lines intersect. And they can be an enlargement, getting bigger, or a reduction, getting smaller. And go ahead and hit pause and copy this into your notes. And again, we can see our pre-image, our starting part. Our image would be our dilation this time. And in this example, we have an enlargement. And then we have the center of dilation there. So make sure you get all that in. Okay, so normally we do this in class, but we can't. So if I measure, so I got something similar to what you just copied in your notes, right? I got triangle RST, it's my pre-image, and I have RST prime, which is my image, and it's been enlarged, it's been made bigger, right? So if I take a ruler and I measure my sides, for example, this side is 1 centimeter, this side is 2 centimeters, and if I do that for all the sides and move the ruler around, I can put my information in the table here. Okay, so now I'm going to do a little math. If I take my image, my enlargement, and I divide it by the same size, so I'm looking at this side right here divided by this side right here, I'd get 2 over 1, which is 2. Same for my STs. I would get 2 over 1, which equals 2. And my hypotenuse is 3 in this case here. And so I would get 3 on this guy right here and 1.5 on this guy right here. And guess what? Still 2. Okay, so what do I notice about these ratios here? They are all 2. Okay, so I know they're the same shape and they're different sizes, so they're not congruent anymore. We're going to call them similar. And we've kind of proved that these guys are similar here because they're the same shape, but they're not the same size, but they're proportional to each other. What about their orientation? Has their orientation changed? That's a big no on that. The hypotenuse is still facing the same direction. The right angle, or we're assuming it's the right angle, is in the same spot as well. Okay. All right, so that's like if you popped out a ruler and measured it, but you can also work on the coordinate plane and see. All right, so I have my starting point here, my pre-image in blue. I have my image in green here. So this time I have a reduction. My image got smaller. So what I did here is I plotted all the points of my reduction here, and I plotted all the points of my original figure, my pre-image in blue here. And let's see what happens when we look at those. So I want to look at my x-coordinates. So I'm going to go prime over the original. Okay, and if I go, my prime is -1 over my original is 2, and I get like about -0.5 there. I'll do that with all my x's. Okay, so I'm going to go 2 divided by 4. Oh, and I'm going to get 0.5. I get 2 divided by 4 again, still 0.5. And then over here I get -2 over -4. Sorry, just kidding. And I get 0.5. So look at that. So the sign changed a little bit there, but other than that, I have all of that. So let's see what happens with my y-coordinates. Okay. I'm going to go my pre-image, I'm going to go my image over my pre-image here. 2.5 over 5, and I get 0.5 again. And then I get 1 over 2, which is 0.5, -2 over -4, which is 0.5, and last but not least, -2 over -4 again, and I get 0.5. So it's the same. So it's gotten smaller, and we have a factor of 0.5 this time. Whereas before over here we had 2, so we had an enlargement, and we could say, hey, it's 2 times bigger. And now this time we have a reduction, and it's half as big as it was before. Okay, because in this case it's hard to tell like how long exactly the sides are. So sometimes it's easy to use a ruler, like when or you can use a ruler, or sometimes you can count on the coordinate plane, but that's not always possible. Like here it's easy to count, but these diagonal ones not so much. So we can compare their ratios as well. Okay, so as we looked in those two activities, the first one was an enlargement, the second one was a reduction, and those numbers we came up with is actually called the scale factor. And that tells us how much the figure is enlarged, made bigger, or reduced, made smaller. Okay. All right, I want you to hit pause, copy all this down. All right, so scale factor tells us how much it's enlarged or reduced. And to find it, we have two methods. If we can count easily on the coordinate plane or bust out a ruler, we can go length of image over length of pre-image. Okay, it's like the finish over the start, so that's the only place you can really mess it up. Or we can look at their x, y coordinates if it's on a coordinate plane. And we can go the x of the image over the x of the pre-image, and the y of the image over the y of the pre-image. Okay. So this one, hey, it's really easy to count the sides. So I'm going to do that first method. And again, if I look back, I'm going to look at the image over the pre-image. Okay? So remember, with the prime notation, that's my image. No prime notation, that's my starting point. That's my pre-image. So let's look at one side right here. Okay, so if the length of this guy right here is 2, and it's 2 all the way around, right? It's a square. The length of this guy right here is 6. So again, I'm going to do image over pre-image. So I'm going to look at my image is 6. My pre-image is 2. And when I divide them, I get 3 for my scale factor. Okay, my scale factor is 3. because I got 3 times larger between this guy and this guy. Okay. All right, now if I look over here, I can count over here pretty easily, but I can't over here. So let's use a point. Okay. Let's use point C because, you know, why not? So this is 2, 4, and then my C prime over here is 1, 2. And again, I'm going to look at image over pre-image. And my image would be my finishing one over here, and then my pre-image would be the one without the prime notation there. Okay, so I'm going to go image over pre-image. So I can take my x over my y, and I get 0.5. And I can also compare, my x over my x and get 0.5. Then I can look at my y's, 2 over 4, and I'm going to get 0.5 there. So my scale factor in this case is 0.5. And look, it's a small number, and guess what? I got smaller from my pre-image to my image. Okay, so your turn. Grab a piece of scratch paper, do whatever method you like, okay? Or maybe try both and make sure you get agreement, okay? Like you can try comparing the lengths, or you can try comparing the points, or if you're like totally awesome, you can try both and you should get the exact same thing. So again, look at these, look at your notes, try to find the scale factor, hit pause, and then hit play when you're ready to check your answer. All right, let's check it out. So first I just did like the length of the sides. So this is my image, this is my pre-image, and so if I do like 2 over 4, for example, on this side, I'd get 0.5. And then I chose 2 points. I chose the e's. And so if I go my image over my pre-image, I get 5 over 10 of either of the coordinates, and again I get 0.5. So hopefully you landed at 0.5 as your method. Okay, this walks you through it. So just on your scratch paper, just write 1, 2, 3, 4, 5, and kind of fill in the blanks as you go, and it'll kind of walk you through finding the scale factor. So hit pause, and then hit play again when you're ready to check. All right, let's see how you did. So I looked at my A's and my B's. I did not also look at my C's, but if I did, I'd find that in all the cases, I would end up with 2. I know it's a dilation because the x-coordinates, the ratios of the x-coordinates are the same, and the ratios of the y-coordinates are the same, or you could have said they're 2 or something like that. Number 3, I forgot, is kind of a pain in the butt. You'd have to do the Pythagorean theorem to figure out the lengths of these, and we're not going to worry about that because we know both methods work, so we're just going to say it's 2. The angles, if I traced one of these angles and lined them up with each other, okay, and I kind of like buddy them up like that, I find out that they are also the same of each other. And then my scale factor, which I found up here, tells me that the scale factor is 2. All right, let's do a summary, and then after this is an optional video. Translations preserve the blank and blank of the figure, but the blank changes. It produces a figure that is blank to the original figure. Okay. Preserves means stayed the same. So what stayed the same? Did the size stay the same? No. Did the shape stay the same? Yes. And what else stayed the same? The way that they face, which is also called the orientation. So translations preserve the shape and orientation of the figure, but the size changes, right? It produces a figure that is not congruent anymore. It is similar to the original figure. All right, hit pause, copy all that business down, and then when you're ready, I have an optional math video for you.
Shorts. Understanding dilations. In math, dilation refers to the process of making a polygon larger or smaller without changing its shape. It's picture day. Kate chooses the package with one photo for her parents, a larger one for her grandparents, and smaller photos for her friends. How can photographers print one photo in different sizes? Dilations. Dilation is where a two-dimensional shape grows or shrinks proportionally from a point called the center of dilation. Here we tripled the original rectangle, and here we divided it in half. In dilations, the dimensions and distances from the center of dilation stay in proportion. The center of dilation can be anywhere in, on, or outside of the shape. Scale factor determines how a shape grows or shrinks. If the scale factor is 3, the dimensions from the center of dilation are multiplied by 3. Different sizes, same proportions, same shape. A coordinate grid can help us see how this works. If the center of dilation is 0, 0, and the scale factor is 3, the horizontal distance from the center of dilation is 3, and the vertical distance is 4. Multiplied by a scale factor of 3, the horizontal difference becomes 9, and the vertical distance becomes 12, stretching the shape 9 units to the right of the center of dilation and 12 units up.
Nice portrait, Kate. Grandma and Grandpa are so proud.
If the scale factor is 1/2, the original dimensions are multiplied by 1/2. The dimensions of the reduced photo are 1.5 and 2. Different sizes, same proportions, with dilations.
All right, well, that's it. I hope you enjoyed learning about dilations. Just one lesson left, so hang in there, guys. We're going to keep going a little bit more with dilations, like how you graph them, how you represent them algebraically, and then I cut the last lesson off after that, so you're welcome. So make sure you come back. Go to IXL and do your practice, and then come back tomorrow and do the very last math lesson of the year. Aw, don't cry. All right, see you tomorrow. Bye.